Okay, so today we are going to be talking about covalent bonding, and hopefully we'll be introducing you to some newer things. I know that we've talked about covalent bonding being the sharing of electrons, and we've even went as far to talk about some of the molecules that form, like O2 or H2, when we were talking about the atmosphere, these diatomic molecules, which we'll be talking about later today. But really being able to understand how they bond together, and maybe some of the stuff that you didn't know before and maybe need to know before we move on with drawing them or anything else. Okay, so this hopefully is something that you recognize from biology. This is a strand of DNA, okay? And of course, half of this strand would be RNA. And this is probably what you saw in biology class, a really nice, pretty picture of this double helixed string with these colors in between base pairs, and they were A's and T's and C's and G's that matched up, and you might have even talked about the phosphate and the sugar molecule that made up the backbone. Okay, and hopefully now you recognize this phosphate molecule to be something a little bit more than just something that's on the DNA. Well, we know now that this is PO4, right? This is a polyatomic ion that is bonded with the sugar molecule, giving DNA its unique shape. But instead of using this picture, I would like to use one that is a little bit more effective for us. So now this is also a piece of DNA. You can see here this phosphorus that we were talking about, and it's attached to the 4 oxygens. Oxygen is red, so you can see these 4 oxygens. And it actually has some dimension, okay? You might not be able to see that 3rd oxygen because, in fact, it is turning. But here you can kind of see all 4. And this is a phosphate, just like you've been using in ionic bonding, okay? And it is attached to carbons that make up the sugar that they're referring to, that are actually in this shape right here with an oxygen on top. So it's 1, 2, 3, 4 carbons with an oxygen on top. So if you can see the 4 carbons with that red ball on top, this is actually the phosphate and the sugar molecule bonded together, making this backbone. Okay, and then we have the A's and the T's. Okay, right through here, the T. We have another, or here's the phosphate and the sugar, and these little unique places here are these molecules that indeed attach to each other because of a covalent bond. Okay, so I guess when I took biology, I kind of thought it was just this magic little key, like they indicate here, but these magic little keys are actually covalent bonds that actually want to bond together. And these are covalent bonds holding this together. And because covalent bonding is so different than ionic or metallic bonding, when they share electrons, it actually gives molecular shape. Okay, and this is a really big part of what this chapter is: molecular shape, being able to draw these. Okay, at one point we're going to be able to look at an element or a molecule. Okay, covalent bonding, that's a molecule, and we're going to know how to draw it. And I'm going to give you the tools in the next 2 videos to really show you how to draw it, but there is going to be a little bit of memorizing involved, of course. Okay, so you can see how things are particular. Like this phosphate, they have particular angles, okay, and they are all the same angle, okay, or these hydrogens, the way that they're coming off, instead of being straight up, they're off to the side, and that is for a particular reason. And this is mostly due to the lone pairs that we have discussed that actually push bonds down. So we take water, for instance. It has this bend in it. This is called a bent molecule because these lone pairs take up space and they push the molecule down. So just like you can see in some of these, they have lone pairs because all of these molecules are bonded happily. And so that means they're following this octet rule and all have the 8 valence electrons that are necessary for them to be happily bonded molecules. And DNA is a unique helix structure that is only specific to DNA. So it's a really neat thing, DNA and covalent bonding and how they are related. Okay, so to really understand how the DNA molecule makes those the helix shape, we need to understand these different shapes here. So there are 8 different basic shapes, and what this is called the valence shell electron pair repulsion theory. And for short, we call it the VSEPR theory. Okay? And basically what that means is because the valence shell electrons, when they have pairs, so the lone pairs, actually push these bonds into very, very, very specific angles. And this is what this is representing here. We can see very specific angles that are being made when these lone pairs are on the outsides of these atoms. Okay? And so we will be having a quiz over this information on Monday. And this chart is also on page 190 in your textbook or on your online textbook. Okay? So I'm basically going to give you a chart, and you're going to have to be able to name these different shapes. Okay? And you're going to be able to give me the Lewis structure, and you're going to have to give me the molecular structure. So I'm actually adding something that the book does not have. It just kind of expects you to know it in the next section. So I'm going to break it down for you. So our molecular first one is linear. Okay, so things like beryllium fluoride, difluoride here. This is a linear shape. Okay, other things that it could be CO2. That might even be an easier one. This one doesn't have any kind of different structure because it's flat. Okay, there's nothing coming out at us or going back behind. But carbon dioxide would be another one that you could draw as an example. Okay, so here, this is linear. 2 double bonds never bend, and so we know this is a linear structure. And we know that the angle, that this has is 180 degrees. Okay, and that's a straight line. That's very specific. And we know these different angles because of math. Okay, because of geometry. And that's why this is called molecular geometry. Okay, so that's linear. These are also go for your diatomic molecules like diatomic or atmospheric oxygen, O2. Okay, obviously anything with 2 atoms by themselves or 2 atoms bonded to 1 central atom. So this is referred to as the central atom. There are no lone pairs. There's no lone pairs on the central atom. This always refers to central atom. Okay, and so just like carbon does not have any central atoms. Okay, this will not be on your quiz. This will be the angle. Okay, so here we'd write 180 degrees. Okay. And this would be the formula example, so you could write CO2 here as well. Alright, trigonal planar, this one's also flat, so I'm not going to redraw this one because it's the same as that one. There's going to be 3 atoms bonded to the central, so whenever there's 4 total atoms, 1 central, and then 3 of the terminal atoms, so we have central atoms, and we have terminal atoms. And terminal atoms just means they're on the outside. So if we have this structure right here, boron is the central atom, and the terminal atoms are chlorine. Okay, they're on the outside and they have these lone pairs. Okay. All right. This angle right here is 120 degrees. Okay. Whoops. 120 degrees. And that's on all three sides. So right in here it's 120 degrees. Right in here it's 120 degrees. And right in here it's 120 degrees. Okay. All right. Our next one is bent. There's a couple of different bent ones. The angular, these two are obviously a lot alike, except for this one has one lone pair on the central atom, okay, and this one has two lone pairs on the central atom. Okay, so this one also has a double bond on one of them because there is only one lone pair. Because if you notice, each of these have to have 8. Okay, so 8 electrons because they're following that octet rule. So fluorine has 2, 4, 6 lone pairs, and then he has this line which constitutes 2 electrons because he's sharing one from nitrogen and they're going back and forth, back and forth. So fluorine has 8. So nitrogen here has 2, 4, 6, 8 because of the double bond, and then oxygen has 2, 4, 6, 8 because of the double bond. Okay, so we have to draw these correctly so that all atoms follow the octet rule. And then we also have to know a few other things that I'm going to talk about in the next slide about what nitrogen likes to do. And I've talked about it a little bit, but we're going to talk about it again. Okay, so tetrahedral is our next one. It has 4 terminal atoms. It has 0 lone pairs, very important. And methane is a great example of this. Okay, and he does actually have a separate molecular structure. So these are the same. The molecular structure is not the same for this guy. Okay, so this one, he's going to have tetrahedral, and tetrahedral actually has one straight up, and then he has one off to the side. He has one off to the side. Okay, and then he has one going backwards, which is a dotted line, and then he has one coming out at us, which is a wedge. So we call this a dot wedge structure. Okay, so Lewis structure just shows that everything is following the octet rule. It's almost like an electron dot diagram, okay, with lines. And then the molecular structure actually shows us more like what the last slide was showing. This is molecular structure. Well, not that one. This one. Okay, this is molecular structure. So if these were just Lewis structures, they'd be flat, and so they wouldn't have any geometry. And that really isn't where we're going. Okay, so we need to know their molecular structure. And all of these angles are 104.5. Okay? And that's on all sides. So we're going to be building some models of these and looking at these. I mean, if you don't understand this perfectly right now, it's not the last time we're going to be talking about it. So don't worry, but you do need to have this down in your notes and at least be introduced to it. Okay, and that's called a tetrahedral. The next one is called trigonal pyramidal. It has 3 atoms bonded to the central atom. And this is typically going to be nitrogen. Nitrogen really likes this one lone pair on top. You can see that he does that a lot. And even in his, when he's diatomic molecule, he has one lone pair. Okay, and that's how he bonds with things. So this one has a molecular structure. Nitrogen has his lone pair, and then this is almost like a tripod, just like your tetrahedral. These bottom ones also go down, and we have the wedge and then the dotted line, and that just literally is like a tripod. Like it has 3 legs that are all equidistant from each other, and these really do get to spinning, and they're really pretty to watch if you were. And then these 2 back ones are also 104.5 from each other. So these lone pairs literally are pushing down these hydrogens just as this other bond is pushing these down. So it's like there's a bond here, even though these are just lone pairs. Okay. This bent structure is the same. It's flat, and it just has that angle of 109.5 in it, and which is just a little bit further than the tripod when it's across from each other. Okay, so the trigonal bipyramidal, these are a little bit more complex. These are actually exceptions to the octet rule. Exceptions, obviously, you can see that there is way more atoms than there's supposed to be for phosphorus. Phosphorus has too many electrons, and if you actually look, there's also another exception right here. We'll be talking about these in another video, but you can see boron right here doesn't have 8 total electrons. He only has 2, 4, 6. So there really is another step to this, and it's a calculation that we need to really help us, because you can't just assume this, but you do need to memorize these basic structures to understand this. Okay, so let me go ahead and draw these two out for you real quick. So phosphorus is our central atom here. There are 5 terminal atoms, so whenever you see a 5 here, you know it's going to be this shape. Whenever you see a 6, you know it's going to be the octahedral shape. And so what this is, it's 1 up, 1 down. So there's a chlorine up, there's a chlorine down, there's a chlorine out to the side, then there's 1 going back, and then there's 1 coming out front. So it's almost like it's this trigonal planar right here turned on its side and laid right here with 1 up and 1 down. That's all it is. So as you can guess, these angles right here are all 120 degrees away from each other. They are the same as this trigonal planar here. And then from here, this chlorine right here, down to this chlorine right here, it's 90 degrees. Okay, and we're going to be building these because I know it's kind of confusing right here, right now. But from the sides down, it's 90 degrees. So if you can think about it like that, you can kind of see how that molecule is forming. And then this last one has 1 up, 1 down, 2 coming out at you in front, and 2 going back. So we have chlorine here. And of course, all of these have lone pairs. You never want to forget to make all of those dots. And all of these are spaced out from each other. The top down to the bottom is 90 degrees, and the side to the side is also 90. So all of these are 90 degrees. These are 120 and 90 degrees. This is 109.5. These are 104.5, and these are 104.5. This is also 109.5. Okay? So you'll need to know the number of lone pairs on the central atom. You'll need to know the number of terminal atoms that are connected to the central atom, and you'll need to know these angles for your quiz. Okay? So this is more of a memorizing thing. We don't have to put it into practice quite yet, but we will be. Okay, the last thing that we're going to talk about is just how some of these really important atoms that are going to covalently bond a lot typically bond. So carbon, you're going to rarely ever see carbon with a lone pair. Okay, it's always going to be paired up. It's going to have shared pairs like it was with that hydrogen in the last slide, or it's going to be double bonded to oxygen like it is in carbon dioxide. Okay, rarely does it ever have any lone pairs, and it's typically a central atom. Okay, so you can always count on it being in the middle. If you see carbon, you know that it goes in the middle. Okay, phosphorus and sulfur, they are going to typically be the central atoms of the molecules that they're in, and they sometimes like to be part of molecules that are exceptions to the octet rule. And you saw that in the last slide when they had numerous terminal atoms that gave them more than 8 valence electrons. And you can also assume that things like carbon that are in the same group, like silicone is going to act like carbon does. So we could have silicone right here, and this could be silicone dioxide with 2 oxygens, or we could have silicone here with 4 hydrogens. Okay, just like the halogens, all of group 7A are going to act similar. All right, nitrogen can sometimes act like his fellow people like phosphorus in their group, but typically he is one that likes 1 lone pair on the top. And we talked about this on the last slide as well. He's usually going to have 3 shared pairs. And this is true if he is bonded to 3 different hydrogens, or if he is bonded to himself in a diatomic molecule. Okay, 3 shared pairs and 2 lone pairs. Each one of them is following those 2 things I just told you. And oxygen, I've talked about him before. He loves being double bonded. Oops, and 2 lone pairs. And if he is not like this, he is fighting to get like this, and he is the reason we have resonance structures that give us polyatomic ions. So he kind of is very important, but when we're in chemistry, it kind of seems like a pain. And then our halogens. So this is like fluorine, chlorine, iodine, bromine. Okay, all of these are going to be single bonded. You're going to have 1 single bond and 3 lone pairs. Okay. When they're bonded by themselves to each other, that's how they're going to bond. If they're bonded to hydrogen, that's how they're going to bond. Notice this is hydroiodic acid here. Just throw that in there. Or if they're bonded to carbon or sulfur or something else, and you have a different central atom, they're always going to have these guys with 1 shared pair and 3 lone pairs. Alright, so we're going to be talking about covalent bonding all of next week, and really going over this more in depthly, but these are the some of the basics that you need to at least start to memorize in order for us to move on. So hope you have a great evening, and I will see you tomorrow.